Welcome everybody to Friday before spring break. It is week 13, day 3. And here is a group, Sims and Jensen and, who's the other one? Dang it. Forgot. Made this, and I think I need to shrink the font a little bit. Segwin's the other one. Yeah, shrink the font down a little bit so it'll fit on the screen. And so, bounce off, watch. When I try walking into the water, bounce. When I try walking into the wall, bounce. You just can't move into it, that's all it means. And so we gain health for the whole team, yay. Walk over that, it gives you a location of a boss combat. Got some treasure here. Monsters don't move, so it's fairly easy to do. When you pick up these treasures, they sometimes give you stuff, they sometimes don't, and they add to your stats. Somewhere on the map, you will find other people to pick up. So there's a hint. Let's see if I can find. Encountered a fog monster. It's a boss combat. Okay. You can visualize that and it'll show the circular linked list. They forgot to set the health of the bosses back up. Oh, I died? No. I still swung after I died. Oh. Sucks to be me. Okay. So... whatever. Yeah, you all know what it looks like. So yeah, it just visualizes circular list with all the members of the party, all the monsters, things like that. We're gonna get some lab time for RPG today. Yeah, around 3:30. I'll turn you loose. But if you have any questions right now, bouncing off obstacles, combat, it's not too bad. Just if you're gonna move on to a spot that has a wall or a water, don't. There you go. Okay. Now, if you make a shared pointer of a base class, can I still access derived class functions if I insert derived class objects? That's actually what we're talking about today. So, sometimes you want to call things on a child class, right? On a subclass, however you want to call it. For example, I made up an actor, a hero, and a monster class. And the actor has, actors, the generic stuff like speed and name. And this I'll talk about in a little bit. I've got some overloads where you can print either an actor directly or a shared pointer to an actor. I'm not really sure if you're supposed to overload that, but I did. So if you see out a shared pointer to an actor, then it will print out all of its stuff. I added a tag function so that you could find out what something is. Technically, you don't need to do that because C++ can do that for you. But, this is fairly common where somebody will have some sort of ID function that will identify yourself so you know what the type is, because otherwise if you shoot somebody, all you'll know is that they're an actor, right? And you don't know if you shot a monster or a hero or a goblin or a wizard or whatever, because sometimes you want to do like double damage against a wizard or something. And so having a tag ID system like this where you can just be like, oh, it's a wizard I shot, do double damage, makes life easy. By default, actors do 10 damage. And then we've got a hero class. Heroes, when they attack, they do 20 damage and they do a charge attack. And so that's a way that you could just have like every actor attack. But if you call it, so if you go through like the whole vector and have the whole vector attack, those that are heroes will do a charge attack and then do 20 damage. And then those that are monsters will do a claw attack and then 5 damage. And so only monsters will do claw attacks, only heroes will do charge attacks, and actors will just do their basic take 10 damage thing. So that's one way you can do that. So you can just have a vector of generic actors, shared pointers to actors, and then when it's the hero's turn, they do specific hero-specific stuff. That's one way of doing it. Now, yeah, so I'm gonna show them that in court. And the other way of doing it is there is something called downcasting, where you can convert an actor pointer into a monster pointer if you know that the thing is a monster. If you are 100% positive that thing is a monster, you can cast a pointer from an actor to a pointer to a monster, and everything will work fine. But you have to be certain that thing is a monster first. If not, horrible things happen. Okay. So it looks like this. Okay. So this is saying for every actor in the vector, and some of the things in the vector are heroes, some are monsters, some are generic actors, right? So we got two monsters in there. We got Grindel and we got Carrot Top. And so we're saying for every actor in the vector, if its ID function reports that it is a monster, then we know it's a monster. And that's one of the reasons why I make these ID functions. There is a built-in way, though, in C++ to do it, which is like that. And so C++ has something called RTTI, runtime type information. And you can get the type of a variable at runtime like this. So it's called type ID, and that is a specific weird object, and you can call .name on it that returns a string that is the name of the class, basically with the size of the class prefixed to it. So rather than hero, it is for hero, because there's 4 letters in hero. Rather than actor, it's 5 actor. So I don't know. But basically it's the name of the class. And so you can use this to find out the class name of the thing if you care about it. Or you can manually do a ID function like that reports the class that it is. And then you can do things like this. So for every actor, this is a shared pointer, right? So instead of auto here, I could have said shared putter, Arthur Dwyer, like this. This would work just fine. Same thing. So for every shared pointer we have to actors in the vector, if it is a monster, if it self-reports it's a monster, then we are going to dynamic pointer cast. So dynamic pointer cast is how you can convert from a shared pointer of actor to a shared pointer to monster. Okay? And once you do that, it changes the type on it temporarily. It doesn't permanently do it, but for this one point in time, it is now a pointer to a monster, and we can call monster-specific functions on it like this. And I think that's what you were asking about, Lopez. Right? Like how, like if you've got all these generic actors, like you can't do any of the cool monster stuff on it, right? Like up here, we've got a cool monster attack. It's not an override function, right? It's just a monster-specific ability. So that's how you do it. So dynamic pointer cast will convert from a shared pointer of actor to shared pointer to monster, and then you can call claw or whatever. Just make sure that it is actually a monster first. Okay. So the other way, there's a lot of ways you can do it. Like you could just have something up in actor, and then the things that override the things in actor call the class specific things. That's another way of doing it, right? So there's lots of ways around this. Remember, the whole point of inheritance is to avoid an if statement, right? Inheritance is for people that are afraid of if statements. Like, it's for people that are afraid specifically of doing this, right? They want the type system to do it for them, and so if you don't like this and you don't like if statements, then the more inheritance-y way of doing it would be like what I did, like this, where I basically say for every person in the vector, a call attack, and then the hero class overloads the attack class from actor. Monster overloads the attack, not class, sorry. The monster class overloads the attack function from actor to do monster specific stuff. And so you can put something in actor and then have the subclasses override it. That's another way of doing it. And you can make something that just does nothing unless it's a monster. Is that good class design? Probably not. I don't know. At some point, you know, at some point things have to do things, and where that thing is always up for debate. Okay. You love if statements? Yeah, if statements don't bother me either, and partly it's just because I worked so long in SeaWorld, and you know, you just have dot class name. Okay, what are you? I am a person. Okay, cool. If their class name is a person, do this. If their class name is a thing, do this. If it's a door, do this. You know, like I'm not afraid of if statements. People who get really deep into inheritance say, well, that's unworkable. You can possibly have working code that works like that, and yeah, 500,000 lines of code, and it was not a problem at all. So, yeah, just depends on your perspective, I guess. It's just funny to me that, you know, what people try to optimize away. And so a lot of people who really like inheritance, they just hate having this. They hate having an if statement based on the type. They just want the type system to do it for them. And I don't know, to me, I've made it work. 500,000 lines of code, not a problem. I don't know what to tell you. Okay, so yeah, dynamic putter cast, and that is the end of inheritance, I think. So I think we're good. One other thing I want to show you is a way that I've moved to doing my stuff, and that is to do a unique ID. So basically every actor that goes into my world gets a unique ID. What is this variable initialized to? Anyone see? Uh-oh. It's initialized right here. So in the constructor, it sets UID equal to actor count plus plus. Okay? So actor count here is a static inline class variable. Okay? And this is some C++ trivia. And so what this does is it creates a variable that is associated with the class, not with individual instances of that class. And so every time you make an actor or a hero or a monster, it will increment actor count by 1. And it defaults to 0 because it's a global. Static variables are globals. Globals initialized to 0. Trivia. But important trivia. So the very first actor you create gets user ID or unique ID 0. The second actor you make gets unique ID 1. Third, unique ID 2, so on and so forth. Now, why do I do this? Well, because right now, the unique ID is their location in the vector, right? But in practice, I would have a hash map. I would have a hash table that uses the UID. A unique ID is unique, hence the U. It's unique. I will hash between the unique ID and the actor, a pointer, shared pointer to actor. And what that does is it allows you to have one actor mark safe from if statements today. That's hilarious. I love it. It's great. What that allows you to do, like, because a lot of times, like, monsters and heroes and things like that will refer to each other, right? So, for example, you have a demon. It's locked on to it sees a human, it sees a hero, and it's going to try to move towards it, frame after frame. It needs to maintain state about somebody else in the world. And that's tricky to do. Because the way that I did it when I wrote my 3D VR game was these things would have a pointer to the other thing. Okay? So if you had a rocket and the rocket would like lock onto a target, it would have a pointer to the object that it was locked onto. And it worked fine until the thing died and was deleted. So now I have a pointer to a thing that doesn't exist anymore. Oops. And, you know, shared pointers will help with that. But when you have a rocket pointing at something, then it won't automatically delete itself because you're still pointing at it, right? And so you can actually cause memory leaks and things like that if you do it wrong. And so what I've moved to doing instead in my own projects is using a unique ID for everything. So every object that I ever create in the world gets a unique ID. They never repeat. It's monotonically increasing. Every time you make a new actor or hero or monster, they're given a unique ID. And because hero and monster inherit from actor, they share the same static variable. And they will, a hero might be actor 5, and a monster might be actor 6, and a hero might be actor 7, and a generic actor might be hero 8 or UID 8. So they never duplicate. And so you use that to find somebody in the hash table. And so, for example, if you have a rocket and the rocket is given a target of monster 7, right? What you can do is you can ask the hash table, give me the location of monster 7. And the hash table can know if the thing's been deleted or not. If it's been deleted, you throw an exception. You handle it cleanly. Pointers, like raw pointers especially, can't tell if something's been deleted. But if you have it in a hash table, then you could very quickly find it. It's an order 1 operation to find the thing. It's not much of an overhead. And give you the X, Y, and Z location of something. If it exists, if it doesn't exist, it throws an exception. And then that handles it cleanly. Either it kills your program, or you're like, oh shoot, I should be checking to see if the thing exists or not. Or you have it, somewhere in your code you have an exception handler that basically will handle it. So if the rocket is tracking after something, the thing goes away, exception's thrown, okay, remove my target, fly in a straight line, something like that. So it's a very nice way of doing things. And if you see this in action, you can see One Punch Man has ID 4, Grindel has ID 1, Billy Wolf ID 2, Generic Actor, Carrot Top. They all have unique IDs. And so if I was doing this for realsies, there would be a hash map for every object in the world, and I would use the UIDs to pull the people out, and I could put a wrapper around that to throw exceptions if they don't exist, things like that. So these are the class names according to C++. So you have 4 hero, 5 actor, 7 monster. I don't know why they put the numbers there, honestly. But my ID system is basically the same thing, except without the number. I don't know. I don't tell you. All right. Yep. So everything kind of works the way that you think about it. We start off by making these people, and you can see it creates them with the IDs in order. I sort based on speed, and now it's sorted by speed instead of by ID. Okay. Any questions? It's kind of a cool little bit of C++ trivia, and it works really nicely. It's fast, easy to find. With objects having pointers to each other just makes me really nervous. Like if they're just, if you have a tree, why should the tree have a pointer to, I don't know, a player? Like, it shouldn't know anything about it. I don't know. So, how difficult is it to make, write, and read a save file? So, there is a whole thing called serialization, which involves like Frosted Flakes, Cheerios, Honey Nut Cheerios. No, serialization. Yeah. Looks like this. That's serialization. So, thank you, Mint Curly. It was a bad joke, but I appreciate the laugh emoji. So, serialization is how you write something to disk. And typically, you will write like a serialize and a deserialize function for your classes. And that's basically what you do. So in order to write an actor to disk, I've got, 3 things here? Name, speed, UID. Okay. And I would write those to disk. And for the overloads, I would override it for hero, and that would also write it a health potion. And yeah. So the hero serialize would call the actor serialize, actor : serialize, and then it would print out health potion. That's basically it. And then for deserialize, like I'd probably print out the ID first. So I'd probably do something like this. I'd probably, let's just do it. Actually, yeah, you could probably use a double F for it, probably. But yeah, let's just do it this way. Void serialize, writing to an out stream. Oops. I technically need a space. And yep. So we will just outs our ID so that we know hero, actor, whatever, followed by a new line, and then we will cout name, not cout, outs, speed, and UID. Something like that. And then your read function would just be the opposite. You'd read the ID first, and then based on what it is, you create a new thing of that type. So if the ID is actor, you make a new actor. If it's a hero, you make a new hero. If it's a monster, you make a new monster. Okay. And then you call the deserialize based on which type it is. Okay. So yeah, you make a file, you pass the file to here, dumps it out for the let's do this more proper, like virtual and its const. That. And yep. And then down in the child class, don't need virtual. I'll leave it in. Whatever. Take it out. A lot of people like leaving it in, like I said. But for me, override means that it's virtual, so you don't need both. So I'm just going to call actor : serialize. So I'm going to call my parent class serialize, which will dump the ID, name, speed, UID to disk. And then I will just do the like that. And then I will output health potion, which is the one actor hero specific thing that is beyond what the actors have. So what the file is going to look like is hero, name, speed, UID, health potion, monster, Grendel, bump, 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 bump. And so when you're deserializing, you just open up and you just keep reading until you're done, and you read the name in first, right? And might need to be a global function, because the hero class isn't going to know the actor class. Sorry, the actor class isn't going to know about the hero class, right? So you can't actually put it into the deserialize here. You might need to make it a global function, like down here. Shared pointer to actor, and deserialize. I stream by reference ends. And basically string s equals read line ends. So we're going to read a line from the file that contains the type ID, and then we do a switch essentially, but not a switch. It's just if statement. So if the ID is actor, and let's do this shared pointer actor ret val equals null pointer. So so if the ID is actor, then ret val equals return value equals make shared actor might have to make default constructors for these guys. No, for now, I'll just do this. empty name, empty speed, whatever. And then we just have one of these for each of the classes: hero, monster, and I don't know if even the object-oriented inheritance people can get away from these if statements, because there's no type yet, right? This is how you're determining the type. Shared pointers are made up by professors to trick and confuse students. No, they're nice, dude. Like, raw pointers are so horrible to work with in practice. It really is. Hero, monster. Okay. So basically, you read a line, If it's an actor, you make an actor. If it's a hero, you make a hero. If it's a monster, you make a monster. And then you would just call retval points to deserialize, and then it would read the rest of the thing. So it'll read the name and stuff like that. And then retval, something like that. Okay. So basically every class would have its own serialize and deserialize function on it. And so basically when you write them to disk, you just say for every actor in the vector, call serialize on it. It'll dump it all to disk. And then when you read back, you call deserialize, passing the file. And you do that over and over again until the file's empty. And that'll give you one thing at a time. You stuff those back into the vector. Is that line constructing the monster? Yeah, it is. But that's what I was saying. Like, I probably need a default constructor because I don't have one right now. So I'm just using empty string and 0 for the speed because the deserialize function would read that, right? The deserialize function is going to read the name and the speed and stuff like that. So is this kind of inheritance easier or simpler in other languages? I feel like I'm making messy C++ code. Yeah, Java is a little bit easier. Java, you don't need to do this make shared and shared pointer stuff. All that would just be actor. You just return an actor. Instead of make shared actor, you just say new actor. And that's the only difference, really. Yeah. C++, it doesn't have reference types the same way that Java does. You can't just like make an actor reference. You know, like you can't say this. Like that's not allowed. Okay, but that's essentially what every non-primitive in Java is. Everything in Java is just a reference. It's a pointer, but they just act like regular variables. So it's a little bit cleaner. Your brain is fried on construction with shared pointers right now. You're just still my code. Sure, go for it. I'd probably make it so that when you do the serialize and deserialize, how would you handle the unique IDs? Would you keep the original ones? That's an interesting question. Yeah. Because what if you've been playing the game and then you load it? Now you're going to have duplicate, unique IDs. So maybe you just give them new unique IDs every time. But if you do that, then you can't, like if a monster has a target of a human, you would have to update that unique ID too. So that'd be something to think about, right? Or maybe you just start the world from scratch when you do load, and then it doesn't matter. You can restore the unique IDs that you had before. You just need to have some ability to set this to be whatever the maximum unique ID you loaded from was. So you need to keep that kind of stuff is annoying to synchronize when you load and save. But basically, drawing the map to disk is pretty easy because it's just the map is just and the map is just a vector chars, right? So all you have to do is say for every char, for every vector, for every char in that vector, print it to disk. Like writing the map to disk is easy. Loading it should be pretty easy too. Yeah, basically that. Okay. So if you guys have any questions about that, let me know. We are going to talk about something new today. Remember, there is extra credit available. There is no homework assignments over spring break. I took pity on you. There is, however, an extra credit opportunity. And the extra credit opportunity is to do 8 easy and 1 medium binary search tree assignment on HackerRank. I have moved the take 2 on the binary search tree to after spring break, the Monday after spring break. So that has been pushed back. I'm almost done grading the take 1s If you pass the take 1, you don't have to do the take 2, obviously. But if you are going to do the take 2, I recommend doing the hacker rank extra credit first, because it will give you more practice on binary search trees. It's one of those things, when you work with recursion, when you work with pointers, you just have to keep working with it over and over. And it's just one of those things where you just have to keep kind of grinding on it and practicing and leveling up. And eventually, like, it just becomes easy after a while. And that's why I give you just a bunch of easy ones to do. It should just be like just getting, familiar and comfortable with it. And by the time you do that, the competency exam should be pretty easy. The programming part of it is like pretty similar to the last one, honestly. So if you do the hacker rank ones, it'll be pretty close to one of those too. Sims was asking earlier in the 12 o'clock class what kind of notes you can have on a competency exam, and the answer is it's open internet, open notes, you can go on the server, write code there. You can go on to Geeks for Geeks and copy code from that, which a lot of people did on the linked list competency exams, and almost all of them got it wrong because they didn't understand what they were copying and pasting. So yeah, if you're free to copy and paste, just make sure that what you're copying and pasting, you understand what it does, because like probably 3/4 of the people who tried copying and pasting code from places online got a 0. Not because they copied, because I don't care if you plagiarize. It's computer science. It's what we do. I care on like homework assignments and stuff like that, but what I care is you can answer the problem. And if you don't even understand the code that you're copying and pasting, that's bad, and so that's a 0. Right? If you're going to plagiarize, at least plagiarize correctly. And an interview, what did you miss? Pointer stuff. Yeah, I do like this wallpaper a lot. Okay. Minkrelli is going to do a study session on Monday, and he will post it online. That will help prepare you for the BST Competency Exam number 2 as well. So we're going to be learning a variant of binary trees today, and these things are called heaps. And so they're very similar to binary search trees, except they're completely different. So let's go over like the data structures we know so far and like what they're good at. So this class nationwide requires you to know just a few data structures. Arrays, which you won't even see on here because vectors are just better. Arrays, linked lists, singly, doubly, circular, whatever. Stacks, queues, binary trees. That's the 5 that you have to know for this class. Okay. If you go to a different institution, they will expect you to understand stacks, queues, linked lists, arrays, and binary trees. Okay. So you have to know what each of those is good at. All right. I think it's criminal they don't teach hash tables, because hash tables are the best data structure. All right. Order 1, insert, search, and delete is amazing. Between vectors and hash tables, I basically got almost all my bases covered. 90–95% of my code professionally is just vectors or hash tables, one or the other. Sometimes both. Okay. But what you need to know coming out of this class is when to use each one of these data structures. Okay. So the advantage of linked lists, they got order 1, insert front, insert back. And if you have a pointer to the middle of the linked list, they have order 1, insert in the middle. Now, decks have order 1, insert front and back. Vectors have order 1, insert back. So the only advantage linked lists have is if you're going to be repeatedly inserting and or deleting from the middle of a list. And in order to get there, you have to do an order n traversal to get there anyway, so the advantage of linked lists is minimal. But like maybe you're doing something like a word processing document, you move the cursor to the middle of the file, you start typing, you want to be able to insert things over and over again in the middle. There you go. Linked lists are your data structure choice. You know, I don't want to completely poo-poo them, but like I honestly just almost never use them. Job interviews. There you Okay, so linked list, that's their advantage. Order 1 inserting in the middle. It preserves order. Order means the order they come in, right? Like you have a movie theater in Curly and people come in line. Back when they had lines, I think it's all digital now. I don't know. But like people would come in line, you have to remember the order they came in, right? So linked lists preserve order, vector preserves order, deck preserves order, queues preserve order. Stacks kind of do so, but backwards. But binary trees don't. Hash tables don't, right? Once you put things into a binary tree, binary search tree, it gets sorted alphabetically or whatever, right? And so it loses the order things were put in. Lines for concessions, yeah, that's true. So linked lists do preserve order, which sometimes you care about, sometimes you don't. Okay. So a vector is fast insertions and deletions at the end, push back and pop back, or order 1, amortized order 1. It has good memory locality. So what that means is something you'll learn more about in CSI 45, 4th semester computer science, computer architecture. But I'll just give you a hint right now. When things are next to each other in RAM, it goes faster. Okay? So your computers have like, I don't know, 10 megs, 20 megs of cache, and cache is like 20, 30 times faster than RAM. And so what happens is that when you load data, it loads everything in RAM around it into cache. And so a linked list, if you have one over here and one over here and one over here, you load something, it loads everything around it in RAM, but it doesn't get the other ones, right? Whereas with a vector, you load one thing out of a vector and it loads all the people next to it. And so you'll get cache hits, which are substantially faster. In CSI 45, we benchmarked the difference between vector and linked list, and it was like a 3 times difference in performance. So vectors were 3 times faster, even though they were both big O 1, I think, for all the operations. Despite them having the same big O time, vectors were still 3 times faster due to the memory locality. Okay. So, and there's probably less news that happen as well. The linked list, you have to new things over and over again. With a vector, you just block, allocate a big chunk of RAM. Okay, growable arrays. So vectors can grow and shrink. Linked lists can too, right? They can grow and shrink. That's nice. They're dynamic. That's why arrays are not on here at all, because arrays just kind of suck. There are some niche cases for arrays. If you want to be stack allocated, use an array. You have to be careful. Don't make it too big, because then you'll stack overflow, right? Stack allocation is slightly faster than heap allocation. So if you're doing it like 1,000,000 times a second, yeah, sure. If you're making like an array of size 100 and you're allocating and deallocating it like 1,000,000 times a second, yeah, an array is going to be better than a vector. Like there are some niche cases like that where there is a spot in the standard library for arrays. In general though, yeah, just use a vector every time. And if you need more speed and you're not going to stack overflow, maybe consider switching to an array. Okay. Yeah, and arrays are fine too if you have a fixed size, then they're small. The trouble with arrays is that, like, yeah, sure, fixed size is okay. But if you have a fixed size of size 1 billion, don't use an array because it'll stack overflow, right? Vectors can handle big things. Arrays, medium to small sized arrays are fine, but a big array is probably going to run you out of stack space. You're probably going to segfault. Okay, so I even have arrays up here. Like there is a spot for them, but they're just not up here. Decks are like vectors, but they have order 1 push front and pop front. And if you need that, use the deck. If you don't need it, use the vector. Why? Because I've benchmarked both vectors and decks head to head against each other. And for if they're just doing like all order 1 stuff, vectors are faster than decks by 30%, something like that. Okay. So yeah. So this slide right here and the next slide, this section right here, is what you're supposed to know when you finish CSI 41. What I want from you when you finish CSI 41 is to come out of this class knowing what all the basic data structures are, and so when you do a program, you're like, oh, this would be a great time to use a whatever. Okay? This is the thesis statement for CSI 41. You come out of here saying, oh, I should use a hash table right now. Oh, I should use a set right now. Oh, I should use a vector right now. Okay? This is the main slide for the entire class. Okay? Binary trees. Login insert, login search, login delete. Login is fast, right? It's not as fast as order 1, but it's fast. For every doubling in size, you only do 1 more operation. That's really good. If you have 1,000 people in your binary tree, you have to do about 10 searches. If you have 1,000,000 people, 20 searches. 1,000,000,000 people, 30 searches to find a person. It's pretty fast. Like 30 is a lot smaller than 1,000,000,000, you know? And so you can also merge sets pretty quickly because they're already sorted, so you can do a zipper merge pretty easily with a binary search tree. Whereas with a vector, if you want to do a sorted merge, you have to make sure they're sorted first, right? And then you can do a zipper merge, a sorted merge together. Sets are always sorted. So anytime you have something that requires your elements to always be sorted, a set just leaps out at me as the right answer, right? Like if you have a prerequisite that your phone book is always alphabetized, it's like, okay, use a set. If you're going to be printing it out in alphabetical order over and over again, set, you know. And then hash tables are the champions at insert, search, and delete. Order 1 insert, order 1 search, order 1 delete, on average. And you can use the standard library one, or you can find faster ones. So honestly, the standard library is not really that fast, but it's order 1, so it's gonna blow away pretty much everything else in terms of running time. Everything except for a faster hash table. Any questions? But hash tables are not sorted, right? So if you need to alphabetize a hash table, kind of can't copy everything into a vector and alphabetize. I don't know. So you know, right tool for the right job. You guys with me? Any questions about the basic things? You might notice that also stack and queue are not up on here. The reason for that is because the vector is a stack. Just push back and pop back. It's a stack. And you can use a linked list for a queue, or you can use a deck for a queue. Push back, pop front. Already covered. Yeah, you have a question, Holman, or yeah, you understand. So this is the class. This is the class. Now, the thing is that insert, search, and delete are not the only things that we do with data structures, right? So there are other operations. For example, what is the minimum element? What is the maximum element? Right? And so for a set, you can find that out pretty easily, right? The minimum element of a set, a binary tree, is you just go down to the left. And the maximum element of a binary tree, you go down to the right. Log in. Log in, find the minimum, find the maximum. For everyone else, it would be order in. Who's the minimum element? Order in. You just hunt through the whole thing, right? Binary trees are faster at finding the minimum and maximum element. Will there be a CE data structure in the future? That's a good idea. Yeah, we can do another CE if you want. Sure. It's a good idea. So, then there's other things as well, right? Like data structures to hold video streams, right? I took a class on multimedia systems, and a lot of it was just data structures optimized for displaying images, displaying movies, which are an interesting combination of keyframes with interpolation frames in between that are very small, because they basically say take the previous frame and then just move that guy's face a little bit to the left, so it doesn't have to have a full picture in every frame. Instead, you have a keyframe, and then you have these frames that just have the difference from the keyframe in them, so it can compress down very small. And if you've ever seen a video stream where it breaks up and you see these blocks sliding around, it looks like all neon colors and stuff like that, that's a corruption in the video stream. And then eventually it snaps back. It snaps back when it hits another keyframe, and it resets everything. So yeah, that's a data structure. How do you get the audio to synchronize with it? That's a pain. That's a data structure. How do you hold image data so you can do like progressive JPEGs, so that an image draws on the screen at low res, then it fills in higher res over time? That's a data structure. How do you hold map data? Like if you're gonna you know, have a map of America and you drop a pin on it and you say find me the closest city to this point, how do you do that? What data structure do you use for that? And there's a bunch of cool stuff like that in what's called computational geometry. And so we do computational geometry to plug IS50A and 50B in IS50B. And so there's all sorts of cool things like convex hulls, where you have, given a set of points, wrap a line around it that encompasses all of the points, that is as small as possible. It's a convex hull, used a lot in 3D rendering, things like that. What about a binary space partition? So if you have a bunch of things in a world, then you can make a binary tree where each point on the tree represents a dividing plane. So it looks something like this. So let's say you've got a box, you got a box, you got a box, you got a box, box. Okay, what I could do is I could take a dividing plane and divide it into the left and the right, and that is the root. This is dividing plane 1, and then everybody to the left is over here, everybody to the right is over here. It's a binary tree, left, right. Okay, and then on this I could do a dividing plane this way, and then everybody to the left is over here, everybody to the right is over here, and so this would be dividing plane 2, and then to the left of 2 is just A, so the leaf is just the box. Over here though we still got 2 people, so we'll do a dividing plane like that. And so this is dividing plane 3. And to the left of it, we got E. To the right of it, we got C. And these things get complicated when the dividing plane has to go through a box, and then it has to split the box into 2 boxes, which is kind of a pain, because you have to glue them back together later without having a seam visible on them. And then you got this over here. And so this is dividing plane 4 here. And to the left of 4 is D, and to the right of 4 is B. And then let's say later on you have a camera, like you have the camera here, and this is how like Doom and Quake and things like that worked, and the camera is looking this way. Well, you can tell what this point is by traversing the binary tree, right? So if you wanted to know like, hey, what's at this point right here? Well, you start with the first plane, and you say, hey, is this point to the left, or is it to the right of this plane? And you can do that with a cross product. Cross product from here to here and here to here tells you if something is left or right. It's a very simple operation. Cross product looks like x, y1, x2 minus x1, y2, like that. Or vice versa, depending on how you want to do it. Very simple multiplication and subtraction. And if you get a positive result, it's on one side. If you get a negative result, it's on the other side. So, okay, it's to the left. Cool. So we move to the left subtree. Okay, we're looking at this one. Is it to the left or to the right? Okay, this point here is to the right of this line here. Let's go to the right subtree. Okay, what about this dividing plane? It's the left or right? Oh, it's to the right. Okay. All right, and then now that we're in the leaf node, we say, hey, is this point within the box or not? It is. Okay, return true. It's within the point. And so you can do that to test, what's out there in the world, and you can also use it to draw the world, because the camera here, which is looking out this way, box A should be drawn in front of box B, and we know that this point here is which is where we are. It's in front of, our camera is to the left of the dividing plane 1, left of dividing plane 2, so it'll draw box A first, and then it marches through the tree in an interesting pattern where it draws the other boxes in an order where B will be drawn behind A, D will be drawn behind A, things like that. So that's how Doom and Doom 2 and Quake worked. Doom and Doom 2 were like 2.5D. Quake was fully 3D. So that's a binary tree. It's a binary space partition. And yeah, it's good to make, really. So there's a lot of interesting data structures out there. And you're going to take data structures again. When you're a junior, you're going to learn about AVL trees. As a junior, which are self-balancing trees, and red-black trees. Self-balancing trees, you'll learn that at the junior level. Hash tables are technically junior level, which irks me to no end, because I think everybody needs to know about hash tables. Technically, you're not supposed to know them right now. I teach them anyway. They're too useful. Okay. So, data structure for today is something called a heap. Okay. So heap is a binary tree, and the heap You know, sometimes we'll talk about stack allocated variables and heap allocated variables. Stack allocated variables are held in a data structure called stack. Heap allocated variables are, they used to be held in a heap. I don't know if they still are. It depends on the implementation. Okay. So what is a heap? There you go. That's a heap. You guys all got it? You can implement it? Good? Done? Ready for break? Just do this. You got it? Cool. All right. Simple. Picture says 1,000 words. Exactly. There you go. It's easy. Just do that. Pile of sawdust. Yeah, there you go. Okay, so a heap is a binary tree, but it's not a binary search tree. It's a different kind of binary tree. Okay? So do you remember the rule for a binary search tree? What is the rule? Everything to the left is what? Everybody to the left is less, and everybody to the right is bigger. Yeah, so the binary search tree invariant is everybody to the left is smaller, everybody to the right is bigger. Heaps are the same thing, except rather than left and right, heaps are up and down. Okay? Huh? Here's the heap invariant. If you have a max heap, there's max heaps and there are min heaps, and they're just sorted differently, in opposite directions. For max heap, everyone below me is smaller. Everyone above me is bigger. Make sense? So the very top of the heap is the biggest. Okay? And so heaps are interesting because you always know where the biggest element is in a max heap. It's at the top, right? The top element would be the biggest element because it is the top. However, if you're looking for a specific number in a heap, you can't find it very easily. Like if you just want to say like, hey, is the number 42 in the heap? I don't know. You know, it doesn't really support that operation. It's not about insert, search, and delete. Max heaps, heaps in general, also known as priority queues, they support just 3 operations: push, pop, and top. Okay, that's it. So they're like a queue. You push things into them, you pop things off of them, and you can ask what's at the front. Okay, and the you can't really search it. There's no search. There's no find. Right. And the reason why they're called a priority queue is because whoever has the highest priority comes to the top. Right. So if you got a bunch of people waiting in line at a nightclub, and Kanye comes up, he gets to cut to the front of the line. So max heaps work like a queue. But if somebody comes in with a higher priority, they come to the front of the line. Okay? So how does it work? Let's take a look. So let's give you a sample max heap here. Okay. And one of the nice things about a max heap is that they are always full and complete. Okay? So if I were to insert something into a max heap, do you see how this works? Everybody up above us is bigger, everybody below us is smaller, but you can see they're not really sorted, right? So we got the number 1, the number 14, 15's here, 5's here, -7's here, 3's here. Like they're not in any sort of sorted fashion, right? It's just sorted kind of vaguely sorted. Bigger things are kind of higher, but like you can see like down here 14 is bigger than 5. But it doesn't matter because it's not in the same branch. It's not in the same subtree. Okay. Yep, the root is always the biggest. In a max heap, it's always the biggest. And so that is the root of our tree. Okay. And one of the nice things about a heap is that it is always a full and complete and balanced tree. Nice property. Okay. The way that it works on a heap is when you go to insert, you insert at the next available spot. Okay. So if we wanted to insert, if we wanted to push, let's say we push the number 0, it goes in here. Now let's say we want to push the number -10, it goes in here. We want to push the number negative 30, goes in here. I'm going to push 10, goes in here. Push 11, goes in here. Push negative 30, goes in here. Do you see how that works? There's always like the next available spot is where it goes. Okay? Any questions about that? There's no way to search, you just have to go through the whole thing. Yeah, it's not designed for searching. Heaps are designed for constantly calling min or max, right? Whichever you have. If you have a min heap or max heap. If you max heap, you're going to call, hey, who's the biggest guy? Who's the biggest guy? Who's the biggest guy? Over and over again. Okay? So that's what heaps are good at. Constantly calling who's the biggest, who's the smallest, depending if you have the max heap or a min heap. Do you have any questions about how this works? There's some very obvious things, some very obvious questions here. Because so far, everything that I've put in just happened to work, right? 11 is smaller than 14, 10 is smaller than 14, negative 30 is smaller than negative 7. Push 19, thank you. There's a very obvious question here, which is what happens when you violate the heap property, right? So if we put 19 in here, have we violated the heap property that everybody above us must be bigger than us? Heaps and AVLs are completely different, dude. AVLs are balanced binary search trees. This is not a binary search tree. This is a heap. They have completely different purposes. An AVL is just it's a way of just making sure your binary tree is always balanced. That one side of the branch isn't more than twice the size of the other side. Okay, so yeah, Portnoy is right. It has violated the, well, yeah, but they have different operations. Like they're just not, they're not comparable. They're not the same. So what we do if we violate the heap property is we swap the values. Okay, so we just do this. And then repeat. Have we violated the heap property? Yep. Swap it again. Bloop. Bloop. You can do this with like 4 lines recursively. It's actually a really easy to write algorithm. And now we're good, right? Because 19 is smaller than 20. And so this is called bubble up. So you insert it in the next available spot and you bubble it up. Okay. So if we were to insert, rather than negative 30 in that spot, if we had instead inserted 30, then we would swap 15 and 30. 15 would be down there, 30 would be here. You check these two. Bloop, bloop. 30, 19. These are violated. 20, 30 swap. And you stop the recursion when you get to root. So when you get to the top of the thing, you're done. Okay. It's not bubble sort. It's bubbling up though. It's similar to bubble sort, I guess, where you swap as you go up the tree. But it's not. Bubble sort goes through the whole vector. The heap only checks log n. So this is in order log n. Okay. What happens with pop? It's very similar, except you're going to do bubble down instead on a pop. You do bubble down. Okay. And so what you do with pop is you only pop 30. Only the root pops off. Okay, that's it. So what you do is whatever the maximum element in the heap is comes off, gets deleted. And so what you do is you take this, whoever is inserted last. In this case, we had negative 7, or whoever was in that spot, right? Gets moved up there. The last node gets deleted, and now you do a bubble down, okay? And so the heap property says whoever is bigger must be on top. So which one of these two children am I going to swap, 5 or 20? So one of these two, because it's smaller than both of them, right? But only one of these will satisfy the heap property. So which one do I swap? 20. Yep. So 20 and neg 7 swap. And then you repeat, recursive. 19 is bigger than 14. Bubbling down is a little bit more complicated because you have to check both kids, right? And so we get a 19 here and a negative 7 here. Check these. And 15 and negative 7. We'll swap. And we're done. That's also order log n. It's just a little bit more code. It's maybe 10-ish lines of code. Okay. And there you go. If we pop again, -7 and 20 swap again. 20 comes off, and then we bubble down again, and you just do that. Like these, or that's the direction that you're going to pop, essentially. That value gets deleted. This value gets put up there. You erase it. And so the really nice feature about a heap is it is always full and complete and balanced. So the tree does not have any gaps in it. It is never unbalanced. It is always perfectly balanced. There are no gaps. And because of this, you actually don't need any pointers. You actually do not need any pointers at all to do a heap. This is typically implemented using a vector. So when you do this, you just call pop back and it deletes the last element. And this actually is really nice for two reasons. First of all, you have the contiguousness of memory. Like everyone's next to each other. It's very cache friendly. Everything's next to each other in RAM. It's wonderful. That's one benefit. The other benefit is you don't waste all that RAM on pointers, right? Because with a binary search tree or an AVL tree or whatever, you've got two 64-bit pointers here, right? You got a 64-bit pointer to the left, 64-bit pointer to the right. You got all these null pointers down here. They're just eating up space, not helping very much. And the int itself is only 4. You know, it's 4 bytes for the int, and it's 8 bytes for each of the pointers. So you've got 16 bytes of overhead to store 4 bytes of data. So you're like 25% efficient, right? With a heap, you don't need the pointers because you're just storing it as just like an array of ints, basically, or a vector of ints. And so it's very memory efficient. You don't waste all that RAM. If you want to know how many levels are in the tree, well, that would just be the log of the size, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We got 14 people in the tree. Where's my calculator? Okay. And we will take the log. It's probably log base 10. 14, log base 2 is 3.8. 1, 2, 3, almost 4. See? So if you want to know how many levels are in the tree, just take the log base 2 of it. It'll tell you. Yeah. If you want to know who your parent is, that's really easy. You can't do that with a binary search tree with pointers, right? Unless you have a pointer to the parent. Wait, what? What do you mean, wait, what? Important enough. And so, like, if you were to do this as a array or a vector, it would look like this. Yeah, it's just the logarithm of the size. That tells you the depth of the tree. So it's going to look like this. 20, 5, 19, 3.1415. It's funny how that worked out. 2, et cetera, et cetera, et cetera. Okay. So index 0, index 1, index 2, index 3, index 4, index 5, index 6, 7, 8, 9, 10, 11, 12, and 13. Now, there is a pattern between the index of a node and the index of its parent and of its two children. It's just a simple algebraic equation. Okay? So here you got 5. And 5's parent is at index 2. 6's parent is at index 2. And so the equation to find the parent is your index minus 1 divided by 2. 6 minus 1 is 5. 5 divided by 2 is 2. 5 minus 1 is 4. 4 divided by 2 is 2. So that tells you the index of the parent. 2 minus 1 is 1. 1 divided by 2 is 0. 13 minus 1 is 12. 12 divided by 2 is 6. See that? So you can find your parent's location without needing a pointer, just a little bit of algebra. And then your kid's addresses, your left shark's address is your index times 2 plus 1. And your right child is at index times 2 plus 2. So if you're at index 2, your left child is at 5, your right child is at 6. So 2 times 2 plus 2, 2 times 2 plus 1. If you're at index 4, your left child is at 9. 4 times 2 is 8, plus 1 is 9. 4 times 2 is 8, plus 2 is 10. So yeah, so basically you don't need pointers. You can just, you know, and if you want to know if your root, well, root's always at index 0. If you want to know if your kid is a null pointer, you just check, you know, you gotta, you do the math. So like the left child of 11 here would be 11 times 2 plus 1, which is 23. 23 is greater than the size of the heap, so it's null, right? So you just use algebra instead of pointers, and it's nice. It gives you really nice performance. It is easy to code, believe it or not. It's actually a surprisingly easy to implement data structure. There's actually priority queue built into the STL if you want to do that. There's also a C version of heaps where you pass it an array of integers and it turns it into heap form. So the first element in the array is the root, and then you got 1, 2, 3, 4, 5, 6 like that. So there's actually some C functions that will do the heap operations for you just on an array of integers. It's kind of fun. So, anyone have any ideas of where you would use this? When would you use a heap? Anyone have any idea? When would you need to know the maximum element? No. These are actually useful, not just for coding interviews. They're not linked lists. So when would you need to know repeatedly, very quickly, who the maximum or who the minimum is? If you have a max heap or a min heap. RAM? Yeah, I don't know if heaps are actually implemented using heaps anymore. I'm not sure about that. It's a good guess though. It used to be. That's why it's called the heap. But I don't know if they actually do use heaps anymore. Anyone have any ideas of when you would use such a thing? When drawing? What do you mean when drawing? Drawing a scene? I'm not following. Sorry. Something efficient like calculus. I'm not following. Stats application, quick access to highest priority, giving the average of something. Grenades, yeah, grenades are, Jensen was in the 12 o'clock class, so he knows the answer to it. You want to make a 3D application, ray trace it. So one use of it is just as a priority queue, right? So you put a bunch of things into a queue, and whichever thing has the highest priority comes out first. And so this is useful in a lot of algorithms. For example, Dijkstra's algorithm, where you're trying to find the shortest path to something. You basically have a bunch of cities that you could drive to, and you want them always sorted by the shortest distance. And so what you do with Dijkstra's algorithm, which you learn about in CSI 26, over and over again, you take the distance to the smallest city off the priority queue. You update the shortest distances to things, add all of the people it was connected to into the priority queue, and repeat until the priority queue is empty. And that is it. That will give you the shortest route from San Diego to New York in a reasonably efficient amount of time. It's as simple as that. And you can implement it just using the priority queue class in C++, and you keep track of it. You have a set that keeps track of who you've seen and who you haven't seen. And you have a priority queue of just all the cities out there, sorted by whichever is the shortest distance away. And that's it. You just constantly pop things off, add all its children, and repeat until the thing's empty. So that's it. Dijkstra's algorithm is really easy. The only people that should get I'm sorry, I been recording. The only people that should get PTSD from it. This last semester, I gave them like 3 different Dijkstra's algorithms. So, no, it takes a lot to wrap your brain around. That's why I gave it to them 3 times. Just keep hammering them until they get it. But it's literally like this is the heart of Dijkstra's algorithm, and you don't need to write it yourself. You just use the priority queue class that's in the standard library. Another example would be scheduling things. If you wanted to schedule, like you've got a bunch of processes on your computer, you want to schedule them, and some things have higher priority than others, use a priority queue, right? So things with higher priority tend to bubble up to the top, and then over time, eventually things with lower priority will get priority added to them because they've been sitting around waiting for a while, and so they'll bubble up to the top, and then they'll run for a little while, then they get kicked out, and then put back into the bottom again. And so task scheduling uses a priority queue, and so you can, for example, on the server, network usage priority, sure. You can see here the priority of different things here. Real time, priority 20 is the lowest priority, actually. Higher numbers are, oh no, sorry, that's niceness. So almost everything's at niceness, 0. I saw down there, yeah, here's something at niceness, -1, so it's negative nice. So that means the task scheduler will give it additional priority. You can see most of these things all have the same priority, but you can, like Linux will give additional priority to interactive applications, so that when you type, your keys instantly appear. They do that because it annoys the hell out of people when you type and your letters lag. And so Vim and things like that will get temporary boosts to their priority when you're typing, and then it loses the boost when you're not typing. And so normally Vim gets the same priority as everything else when you're typing. The Linux kernel will actually give you more time and make it more responsive and things like that, so that you have the illusion of the system being very fast and responsive to your needs. Yeah, load's pretty good right now. Okay. Negative niceness. Yeah, if you want to run something with negative niceness, you have to have root. So only people with root access can run with negative niceness. And so, like when my students are hammering my server, I'll run my stuff with negative niceness, so it doesn't lag me. You're all blessed to have 26 in person. Yeah. Does clear lag the server? No. This clear echoes a single character to the screen. It echoes the VT100 escape sequence. It's about 5 characters. That's it. Clear will not lag the server. Running your hash table assignment will. So, yeah, the example I gave in CSI 41 at noon was an example from like video games. And so what happens in a video game is that the server maintains the current time, right? It's like the current time might be 10.1, right? It's been 10.1 seconds since the game launched. And every object in the world has a next think, which is a double, basically. And it's got a think function, which is a callback function. And so anytime you do delayed execution of something, like a grenade, that's what Jensen was talking about earlier, you pull the pin on the grenade, you throw it, and you say in 3 seconds, I want you to explode. And so this will go into a priority queue, but it's going to be a min heap instead of a max heap. And so if you put that grenade and you say go off in 3 seconds, the current time is 10.1, 10.1 plus 3 is 13.1. So what you have in your min heap is 13.1, and it'll have a callback on it, which is like the explode function or something like that. And so maybe throw a few more grenades, and you got one at 14.1 and one at 13.2 and 17.1 and 20.1. I don't know why they're all 0.1s, 0.6, whatever. And all of them, these are all just grenades. And so at time t equals 13.1, you should have an explosion. 14.1, 13.2, these are the times when the grenades will explode. Now, what happens is you could have a lot of things in your world, and it's really, really slow and inefficient when the time ticks up from 10.1 to 10.2, because maybe your tick rate is 10 frames per second, right? Somewhat common for video games, right? The server will tick 10 times per second, and it will update the time. 10.2 becomes 10.3, 10.4, 10.5, that kind of stuff. And what you do every time you tick is you could, if you wanted, check every object in the world and see if they have something to think, right? You could do it. You could do that, and it would be order n every time. You have 1 million objects in your world. Every frame, 10 times per second, every frame, you check all 1 million things in your world to see, hey, are you going to explode? No. Are you going to explode? No. Are you going to explode? No. No. Or you can use a priority queue. And so a priority queue, instead, all you have to do is check the root, right? 10.4, hey, is there anything to be done? Nope. Move on. Right, that is order 1. Is there anything to do? Nope, move on with your life. All right, it is now time 10.5. Anything to do? Nope, move on with your life. What about 10.6? Nope, nope, nope. You can check all 1 million objects in your world in one single operation because all the people in this heap are going to be bigger than me, right? This is a min heap, right? You guys get that? It's pretty cool, right? It's pretty cool. You can have a queue of all the things that are waiting to do stuff, and all you have to do is check the very first thing because they don't move. Yeah, these things don't move. All that happens is that every time the server ticks, you don't need to subtract any of that stuff. These are just timestamps, right? At time 13.1, it's going to explode. And the server just keeps track of the current time, 10.6, 10.7, 10.8, and all this stuff just sits there. It doesn't move. Nothing in here changes. But once you get to 13.1, right? Once the time finally hits 13.1, it checks the top. It's like, aha, there's something to go. And so it calls this function, calls explode, it does its thing, it damages people or whatever. And then it pops it. So it's going to swap the last element. Oops. That's not the last element. This is the last element, 20.6. So that is going to swap into the root. And then it's going to do a bubble down. So it looks at the two people here. You're smaller. And we're done. Now, on the next tick, 13.2, another grenade is going to go off, right? And so, bloop, that's going to get erased. The last person in here, 17.1, comes up to there. And then we look at the 2, and we're like, okay, fix the heap condition. And we're done. And then 13.2, 13.3, 13.4, 13.5. Nothing, 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 nothing. And so it makes it very efficient to do things like that, where you have things that are going to take place in the future, put them into a min heap, and then all you have to do is check one thing, most frames. Worst case scenario, everything goes off on this frame, sure. But you're going to be doing a lot of checking, usually, before something actually happens. You might have 100 frames or something between things happening. Okay. Can I add 17.1? It's already in the heap. Sure. Okay. There you go. So it's a priority queue, right? So you'd probably need to, I don't know, handle ties somehow. It'd just be fine. I don't know. Depends how you implement it. So it's log in when something happens, and it's order 1 when nothing happens. Yeah, and because nothing happening is the common case, right? Order 1 is the way to go, right? That's some, you're just calling min. That's the dominant activity. Calling min over and over again. What's the smallest thing? What's the smallest thing? What's the smallest thing? And every so often you do an order log in, and that's fine. Okay. How would you link a callback to the queue and heap number? This would be a struct, and it would look. Did I log off again? Check me out. All right. Discard. So functions can be held a couple different ways. The C++y way of doing it is, I think it's held in functional. I'll have to check the reference for it. I'm sorry, I'm cutting into your lab time, but it's a good question. So let's see if you reference function. It is in functional. Okay. And so you can actually make variables of type function, std function. And the template parameter for it is what kind of function it is. It's a void function that takes an integer as a parameter. And so that's the variable name, and it's setting the variable equal to that function there, print num here. And so you would just basically pass that to the struct. Okay, so look like this, struct heap node. And it'd be double next think and std function void just a void function that takes no parameters. And think, and then so node A is equal to, at time 10.1, I want you to, let's make it a grenade. Right. Just like that. And then you just put that into the priority queue. And the priority queue you have set up to sort based on next think. You use a comparison function, right? That. And I think priority queues might actually sort greatest to smallest by default, so you might want to switch that after you test your code. But basically, yeah, that's all you do. And so you just make a bunch of nodes, add them into the priority queue, give it this comparator to sort the priority queue, and then just every, you do like a while true, time plus equals 0.1. And then you can just like check, I don't have the priority queue, priority queue dot top dot next think. It's greater than time, then continue. You do something like that, right? So basically, just and every frame it's going to be doing all the physics of all the objects in the world. It's going to be reading input. It's going to be handling client connections. It is connections. It's doing a lot of things every frame. But basically every frame, if you have a tick rate of 10, time will go up by +1. And then you just check the top of the priority queue and just see if there's anything to be done. If there's not, just move on with your life. If there is, then you will pop things off, call the callback on it, etc., etc. And so you could say like a dot think, like that. And that's how you call a function. That's how you call a callback. That easy. Kind of cool, right? Yeah. So, yeah, I don't have the priority queue in here, but that's basically it. You just you know, every time somebody makes a deferred action, something that will take place in the future, you throw it onto the priority queue. And then the server will just check the top of the priority queue and be like, is there anything to be done? Nope. All right. If there's something to be done, it calls the think on it and it pops it off. The it'll call, you know, basically priority queue.top think, and then it will call priority queue pop. That's it. So while at least something like this. So while there's things left to do, call the think function on it and then destroy it. And that's how you can queue up actions to take place at later points in time. It's very simple, very fast. Okay. Is priority queue your next homework? Sure, if you want it to be. We do something like that. Okay. They're fun. They're fun. Okay. So that is it for today. You have half an hour of lab time. So have at it. RPGs will be collected promptly at midnight tonight. If you have any questions about the RPG, I will be here. But I'm going to turn off the recording because me staring blankly at the screen for half an hour is not good television. I heard somebody trying to speak. Truman Show. Weatherby. Hey, Shelby, how you doing, man?
I thought I'd crash class dissertation. It's all great to me.
It's all good. We're just starting spring break, I think, in half an hour. So they're making role playing games right now.
That's fun.
Mm-hmm. It is. So yeah, I'm gonna sign off, I guess, now, and I'll just stare at the screen for the next half hour. All right. Peace out, everyone. Bye. Have a great break.